Hello everyone and welcome back. Now, in the last video I introduced to you a method of solving differential equations using series expansions or power series, Taylor series. Now, I give you a very basic example, right? One of our favorite second order differential equations, the second derivative is equal to the negative of the original function, sine and cosines solving this for us. We saw how to expand it. But what we're going to do in this lecture is look at solving a much more complex differential equation where we do not have access to a non-series solution. Now, this differential equation is a very famous differential equation, and it's called Airy's equation. And it is a second order differential equation. It looks relatively simple. It is the second derivative minus x times the original function is equal to 0. Now, you can try all you'd like, but we do not have a closed form for the solutions, right? It's not like e to the minus x squared or something like that. You might be tempted to say it is, but be careful, second derivative here. So the best that we can do is find a series solution. What I'm going to do today, I'm going to solve this in two ways. I'm going to center it around x equal to 0, and I'm also going to center it around x equal to 1. Now, let's start with x equal to 0 and see how this all works out before we get too excited. So here's what I want to do. Remember, I'm going to set y is equal to the sum n equal to 0 to infinity of an xn, right? We're centered around 0. Well, if you go back to the previous video, we did the derivation of the derivatives. I'm going to just go ahead and give you what the second derivative is. And this will be moved around so that I start at 0 and I have, again, a generic term that is in terms of x to the power of n. So an plus 2 x to the n. Okay, let's put this into the differential equation. So let's say put into ODE. On this case, I get 0 is equal to y double prime minus xy, which gives me, so here's my second derivative sum, n plus 2, n plus 1, an plus 2, xn. And then I get minus x times another sum. So I'm going to go ahead and put the x into the summation right away. So I get an x to the n plus 1. So the plus 1 is coming from multiplying that x in. If that wasn't there, I would just have my original y. But now this is making things a little bit ugly, because technically this series starts at n equal to 1. I want them to have the same generic term. So let's do something here. Let's start with this piece. I'll start writing that first. This is the same as counting from 1 up to infinity of an minus 1 x to the power of n. I wanted x to the power of n because I have an x to the power of n. Same generic term for both of these series. Problem is now I'm starting counting at 1, whereas here I was starting counting at 0. That's okay. I can take the first term out of the sum. So at n equal to 0 here, I get 2 times 1, that's these pieces, times a 0. And now I can write the rest of the sum starting at 1. Why? Because I took out the n equal to 0 piece right here. So I get n plus 2, n plus 1, an plus 2, xn. Now this is a saving grace for me because this gives me 2a0. And now I can put both of these series together. N equal to 1 to infinity, n plus 2, n plus 1, an plus 2 minus an minus 1. All times x to the power of n. Well, in this case, what I can do is, again, it's set equal to 0. So let's put the 0 here as well, just so that we can all see it. Now, what we know is that if you have a power series equal to 0, it means every single coefficient has to be 0 as well. So, first thing first, A0 is equal to 0. Pardon me, this should be A2, right? Let's be careful with this. N equal to 0 gives me A2. Now, A2 is equal to 0. That's OK. Now, the rest of this is going to give me, now I get n plus 2 times n plus 1, an plus 2 minus an minus 1 is equal to 0 for all n greater than or equal to 1. I can rearrange this a little bit. I get an plus 2 is equal to an minus 1 divided by n plus 2 times n plus 1. So it kind of looks similar to what we did in the previous example, but there's no minus out front. And this is actually a third order difference equation, right? Because there's a difference of 3 steps between these two pieces. In particular, if A2 is equal to 0, so this piece right here, this gives me, so if I go 3 steps ahead of that, I get A5, which from this relationship gives me A5 is equal to 0 too, right? Because I get A2, which is 0, and then that gives A5 is equal to 0. But if I go 3 steps forward again, A8, again, it has to be equal to 0 from A5 equal to 0. Similarly, A11 is equal to 0, and so on and so forth. Every third A value is equal to 0. And that comes from exactly this piece right here. Now, what about the rest? Well, let's look at when n is equal to 1. That gives me A3. And in my case, I get A3 is A0 over 2 times 3. Similarly, A6 is equal to A3 over 5 times 6, which is the same as A0 over 2 times 3 times 5 times 6. And you can see that this is getting very, very ugly, right? They're missing a 4, so that's not really 6 factorial. And another one we could have is A9 is equal to, so in this case, A6 divided by 8 times 9, which is A0 divided by 2 times 3 times 5 times 6 times 8 times 9. So you're missing 4 and 7 to have a proper factorial here. Now the other thing you probably saw, when you probably noticed this, I started writing them ascending instead of descending. The reason I did this is because I wanted you to see the pattern of skipping the 4, right? It's easier to go up with these numbers than it is to come down. So you probably, when you saw me do this right off the bat, you probably said, what's going on here, right? This feels a little different than what we did with the last example. But it's mostly just to emphasize to you the gaps. I think it's easier to see those. Okay, so what does that give me? Well, in general, I get every third coefficient, so A3n, is equal to, now it's much more complex to write down, so I get A0, and then 2 times 3 times 5 times 6, and you keep doing that alternation until you get to 3n minus 1 times 3n. Right, so you're multiplying in these pairs, but it's in a very precise way. You skip every third number here. And this is valid for all n greater than or equal to 1. Okay, so in the same vein, you can do this for A4. So A4 becomes A1 divided by 3 times 4. We're going to have these gaps again, so I'm going to write them in ascending terms. A7, well, this is going to be A1 divided by 3 times 4 times 6 times 7. So we're missing 5 now. And I went ahead and just jumped through with it. I didn't put the A4 intermediary term in there. It's just for simplicity. Similarly, A10, this is going to give me A1 over 3 times 4 times 6 times 7 times, and then it's 9 times 10. All right, so again, you're seeing those pairs of integers being multiplied together, and then you're sort of skipping every third integer, right? So we don't really have a nice way of writing this. It's not like our usual factorial that we're used to. So I don't really have any advice beyond just writing it like this. But in general, I get this. A3n plus 1 is equal to A1 divided by, now we've got this weird pattern, 6 times 7, and then keep going up, and I get 3n times 3n plus 1. Now, a few things to note. First of all, the pattern is actually not that complex, right? So for example, if I wanted to generate up these things on a computer, I mean, this is pretty easy to program in with a for loop. So that's not bad, right? Take the previous one, multiply in 3n times 3n plus 1, save that number, push it back through the for loop. You can do this very, very easy. So I can generate these coefficients quickly and efficiently, even if the pattern is a little ugly. Second of all, we're seeing something that we saw in the previous example too, from the previous video. A0 and A1 float through. Those are the coefficients that are used to satisfy the initial conditions. They are going to float through to the very, very end. In particular, we can actually just jump right to the general solution. So the general solution is going to be, so I'm going to write it out as a big long sum. If you put these into this thing right here, these guys have the power 3n plus 1. These ones have the power 3n. And everything with a 3n minus 1 power is equal to 0. So it's easier to write this as a sort of expansion as it is to write it as a sum. So let me show you. The A0 term, so that's all of the 3n ones, I get 1 plus x cubed over 2 times 3 plus x to the 6 over 2 times 3 times 5 times 6, and so on and so forth until we get to the general pattern, x to the 3n divided by 2 times 3 times 5 times 6, and then 3n minus 1 times 3n. And this is an infinite series. I have a method of generating every one of these. Again, if I want to put this into a computer, I can truncate at some value, and I can approximate it by this piece right here. And then plus A1, same thing. I get a 1. Or sorry, I get an x because I have a power of x, pardon me. And then plus x to the 4 divided by 3 times 4 plus x to the 7 divided by 3 times 4 times 6 times 7, just this term right here. And then let's do the general term, x to the 3n plus 1 divided by 2 times 3 times 6 times 7, and then 3n times 3n plus 1. Again, if I wanted to put this into a computer and plot these things, I could just go to a high enough truncation for my power series, generate up all those terms using a computer, and boom, there it is. I've got what we call the Airy functions, right? So this can also be written as y1 of x plus a1 times y2 of x. Now it's written in the form that we're very, very used to, we're very comfortable with when it comes to second order equations. Now the question is, these are series solutions. what values of x do they actually converge for? So let's pose this as a question. What is the radius of convergence for y1 of x? Right? This is an important question, right? We generated a series solution of this thing. So what is the solution, or where is this thing valid? What values of x does this actually work for? Well, let's use the ratio test. So remember, we have the ratio test. It tells us where you converge absolutely. It also gives you the radius of convergence. Let's look at this thing. I get the absolute value of x, and then a3n plus 3 divided by a3n. So I'm just using the terminology from up here, right? The next term divided by the previous one. Well, let's take the x out, and then times the limit as n goes to infinity. Now, the only difference is the extra term that's being multiplied in here. Once you simplify that out, you're going to get 3n plus 2 times 3n plus 3, all in the denominator. Now, taking n to infinity here is an easy thing to do because it's just going to sink this fraction to 0. And this is equal to 0 for every value of x and r. So, what values by the ratio test does this thing converge for? Well, since the limit is less than 1 for every value of x, converges absolutely for every single value of x. So therefore, y1 of x converges for all x and r. And it turns out that you can do exactly the same thing. So similarly, y2 of x also converges for all x and r. So both of these things converge for every single value of x and r. They are valid everywhere, just like sine and cosine functions, even though they're very, very weird, right? The x's come in powers of 3. Same thing here. So it's not really like what we're used to, right? Sines and cosine, you get even and odd powers. Here, you're splitting powers into if they're divisible by 3 or if their remainder is 1. That's kind of weird, right? But nonetheless, these are perfectly valid functions. These are what are known as the Airy functions, right? So Airy function 1, Airy function 2. The reason for that is because they are solutions to Airy's equation. So you can maybe pause this video and type into Google Airy's functions, and it'll show you what these functions look like. I'm going to spare you my very poor drawing skills. I'll put a link in the description to this video to some pictures of what these functions look like, but they are very, very weird. They're not the kind of functions that you might be used to looking at. They oscillate for all negative values of x, but for positive values, they just skyrocket to infinity. They look like exponentials, for example. So looks like sines on the back, looks like e to the x on the front. Very, very strange, right? Because sine is sort of like an e to a complex number, whereas, e to the x is e to a real number. So there's a very, very strange distinction here. These are still perfectly valid functions. They're described by series. We have a way of addressing whether or not they converge and where they converge. In fact, they're valid everywhere. These are perfectly acceptable as functions, even if they're not the kind of thing that you are used to dealing with. Okay, so think about the last example with Airy's equation. I made you center it around x equal to 0. Why? Personally, I like 0 as a number. I think it's an easy number to work with, but maybe you want to center it around something else, right? This is something we can do with power series. Power series can be centered around any point in the domain. And so why wouldn't we potentially want to center it around x equal to 1 instead? Let's walk through it. Let me show you what happens if you take Airy's equation and you center it around x equal to 1. So about x equal to 1. Now, I want to, before we even get started here, I want to emphasize something to you. The power series solution is going to look very, very different, right? Because it's not centered at the same point. Same thing, if you try to do a power series solution of sine or cosine around x equal to 1 or x equal to -3 or something, it's going to look very different than the one that you are used to. We typically center things around 0 in math because it's easy. But we can always center around any other point as well. So I am going to get solutions to Airy's equation doing this, but they are not going to look like the ones that we just saw in the previous piece or the first half of this video. So here's what I'm going to do. Same old thing. I'm going to set my series solution to look like this, centered around 1 now. So I have powers of x minus 1 to the n. Now, taking two derivatives, again in this case, basically does the same thing. N plus 2, n plus 1, an plus 2, x minus 1 to the n. Right? So what I did is I took two derivatives and then I reoriented the indices so I have a generic term of x minus 1 to the n. Same thing I did with the previous example. The only thing that's changed is x minus 1 in there. Okay, let's put it into the ODE. So put into ODE, right? We see this over and over and over. We got a form. 0 is equal to, so first of all, y double prime minus x y. Now we can see where things are going to get weird. So n plus 1, an plus 2, x minus 1 to the n. Now minus x, n equal to 0 to infinity of an, x minus 1 to the n. That's not going to go in the same way that it did last time, right? There's an issue here. I can't just multiply this in and add 1 to the power like I did when I was centered around 0. So the question is, how can I fix this? Well, we're going to do a little trick. We're going to write this. Well, we want to center this thing around x equal to 1 as well. So we want to write x equal to x minus 1 plus 1. This is now a series expansion, a finite series expansion, with constant term 1 and linear term x minus 1. So if I do that, I get now, again, the sum from 0 to infinity of n plus 2 times n plus 1, an plus 2. So nothing changed on the first piece, the second derivative piece. Now, if I replace this x with x minus 1, I can multiply the x minus 1 in. So the first piece, an x minus 1 to the n plus 1. That's from multiplying the x minus 1 in. Then I also have this plus 1 left over. Sorry, this is going to be minus 1 and minus the sum an x to the n. X minus 1 to the n, pardon me. See, even I lose track of this. This is why I like making it around x equal to 0. Now, in this case, the generic term is 1 power higher than everybody else. So I would like to be able to start things at x equal to 1. So let's pull everybody together that has a generic term of x minus 1 to the n. That's these two. So n equal to 0 to infinity, n plus 2 times n plus 1, an plus 2 minus an. That's from this piece right here. And then x minus 1 to the n. Now minus, let's shift the indices on this one. N equal 1 to infinity, an minus 1, x minus 1 to the n. So it's very similar to what we saw previously, but now we have this new term right here. Technically, that's the only sort of new thing that we have. And it came from this special little expansion of this term x, right? We saw that we got an extra term hanging out on the back. Now what we're going to do, we're going to do the same little trick that we did last time, right? This one's starting from n equal to 0. This is starting from n equal to 1. Same generic term. Open it up and then start counting at 1. So now I get 2a0 minus a1, or sorry, 2a2 minus a0, pardon me. That's from setting n equal to 0 in here. Plus, now I've got a sum starting from 1 to infinity. Everybody got the same generic term. Let's put it all together. N plus 2, n plus 1, an plus 2, minus an minus 1. And now what we can see is we've got a much more complex equation. Because, again, remember this was equal to 0. So that tells us that each term in the expansion is equal to 0. So therefore, 2a2 minus a0 is equal to 0, which tells me that a2 can be written in terms of a0. That's good because what we've seen over and over and over again is that a0 and a1, they function like my coefficients that give me my initial conditions. So that's one piece. Now the other piece is this thing right here, which simplifies to an plus 2 is equal to an minus 1 plus an divided by n plus 2 times n plus 1. So this is going to get pretty ugly pretty quickly. I'm going to warn you, unfortunately, there is no closed form for the ANs here anymore. So this is one downside. We shifted what we're centered around, and we sort of lost a lot of the ability to get a solution. But I do want to remind you, you do have a recurrence relation here, right? So you could, again, put this into a computer. This is just a for loop in action, right? As long as I know what's going on at n minus 1 and n, I can get what's going on at n plus 2. So it's not bad, right? This is a very, very computational method. This lends very nicely for me to solve these things with a computer. As soon as I get down to the recurrence relation, then I generate up the terms to any accuracy I want, and I can show what these solutions look like. I can plot them. Okay, this is, in this case, for all n greater than or equal to 1. So let's start counting them up. N equal to 1. In this case, I get a3 is equal to a0 plus a1 divided by 3 times 2. And unfortunately, I'm not going to find a pattern. I'm going to warn you right now, as I did before. So I might as well just go ahead and multiply those two things out. Let's keep going. N equal to 2, pardon me. So I get a4, and this will now give me a1 plus a2 divided by 12. But I know what a2 is in terms of a0, so this gives me a0 over 24 plus a1 over 12. Let's keep going. Let's do another one. N equal to 3. I get a5 is equal to, now a2 plus a3 divided by 20, which in this case, a2 is given by a0 over 2, so I get a0 over 40. And then I get a3, which is right here, which is a0 plus a1 divided by 6. And then times 20 is 120. So that's my a3 term. And of course, I want to group all the a naughts together. So a0 over 30 plus a1 over 120. So it's getting very, very ugly. Again, I do not have a prescription for you of what these things look like or what the general term is. But nonetheless, again, we have a recursion relation. So let's go ahead and look at it. So the best we can do is we can say y of x is equal to, okay, well, what we do is we put this into the sum. So we say sum of n equal to 0 to infinity, an x minus 1 to the n, which is the same as actually expanding out. You know, we have all the way up to a5, so we might as well use it. Well, I'm going to get, after factoring everything, a0, so taking all of the terms with a0s in them, and then multiplying it against 1 plus x minus 1 squared over 2, that's the a2 term, a2 over 2, plus x minus 1 cubed over 6, that's a0 over 6 from the a3 term, plus x minus 1 to the 4 over 24, that's this term right here, plus x minus 1 to the 5, and then over 30. And it's got to keep going. I don't know what the pattern is. I'm not sure that there is a precise one. Nonetheless, I've got the first 5 terms. Same thing, plus a1. And in this case, I've got x minus 1, that's the a1 term, plus, now the next one I see is on a3, so I get x minus 1 cubed over 6, plus x minus 1 to the 4 over 12, plus x minus 1 to the 5 over 120. So it's pretty ugly, but it's doable, right? At least I can get the first 5 terms here. In fact, you could get way more. I just stopped myself at a5. If I asked you to get a6, a7, a8, a9, a10, I mean, it might be a pain, but you could do it, right? There's nothing stopping you from putting it into these formulas and sort of plug and chug, work through this until you get to the solution. Now, in this case, checking the radius of convergence is very, very difficult, okay? So later on, I'm going to give you some theorems that are actually going to be applicable to this situation. You're going to be able to tell me this thing is convergent for every value of x and r. But for now, because we don't have a formula for the general term, radius of convergence will be very, very hard. But here's the cool thing about these series solutions. If I call the first one y1 of x, I call the second one y2 of x, I can check the Wronskian of these things super, super easy. So let's do the Wronskian of y1, y2 at x equal to 1, right? Because that's where I centered around. So clearly I want to do it at x equal to 1. Well, this is the determinant of y1 of 1 divided by y1 prime of 1, y2 of 1, y2 prime of 1. y1 of 1, well, if I put 1 in here, everybody disappears except for the first term. So that's a 1. Then, what is y prime of 1? It's whatever the coefficient on the linear term is. There is no linear term, 0. Similarly, y2 of 1, I get all zeros, right? Because the leading term is linear. Then, what is the y2 prime of 1? Well, it's just the coefficient on x minus 1, which is 1. Look at how easy that was. Turns out that even though series might take a lot of work to work through, the Wronskian is the best part. That's the payoff at the end because it's super, super easy. You get this beautiful little identity matrix coming from the fact that your series solution automatically gives you everything that you need in this. Now, if you're going to use a different value of x in here, then that's very, very difficult. So clearly you need to use the x that you are centering yourself around to make your life easier. Otherwise, I can't help you. Okay, when we come back in the next video, we're going to start talking a little bit more about the theory and in particular address how we know that this thing converges for all x.